So in this lecture, we're going to cover some more concrete topics related to the last lecture. Hopefully this is a brief video. Last lecture was more of a story, but I want to talk about some hard topics that we should really take away from thinking about how we got to this state, how we got to homochirality. So getting into it, I just want to remind us that where we were at, and this is take two. I just did a really long recording without my microphone on. Awesome, right? Anyway, no worries. Okay, no worries from my part. So what I'm getting at is, and what I was trying to get at in the last lecture was we have the origin of the universe. And then from the origin of the universe, we need to get to the origin of life. And I'm leaving a big space in here because what I wanted us to recognize is that as a result of thinking about these things that we talked about last time in the last lecture, we need to have a bridge between the origin of the universe and the origin of life, which involves the origin of homochirality. Homochirality in the universe. Okay, so to get to life as we know it from the universe as it used to be, it's not just about making the bonds and connecting the appropriate elements together. It's about the three-dimensional arrangement. It's actually fairly easy to generate our chiral molecules, but it's really hard to generate our chiral molecules as single enantiomers or to get to homochiral samples of these single enantiomers. So we should capture that. The issue is that racemic product mixtures of biomolecules form when we try to replicate prebiotic conditions. Okay, so the big takeaway there is racemic mixtures of products. So how did the universe achieve homochirality on this planet? That's a really good question. Okay, well, the true answer is we don't know for sure yet. We'll get there. We will certainly get there. We have figured out very difficult, very intellectually challenging things about our existence. We can figure this one out too. So we don't know for sure yet. Okay, but we do, or we have identified some likely steps along the way that will get us there. So the likely steps that the universe, we don't know the mechanism, but we just know the steps that it took to get there. We just don't know how it pulled it off. It's kind of like saying, oh, I don't know. Let's just leave it at that. We know the steps, or we can propose the steps, but we just don't know how the universe pulled it off. So the likely steps are, without further ado, there are three of them, and we'll just kind of provide them and define them. The first step is deracemization. So in deracemization, what we're trying to do is get a slight excess of one enantiomer over the other. So we want to convert a racemic mixture, which is a one-to-one mixture of both enantiomers, into a mixture slightly favoring one enantiomer. Okay, so slightly favoring one enantiomer. This is a term called a scalemic mixture. A scalemic mixture. So what we do in deracemization What we do in deracemization is we try to go from a 50-50 mixture to a, for example, 51-49, or even 50.0001 to 49.9999. I think that's right. Yeah. So because the number of molecules gets to be big whenever we're doing chemistry. I mean, a mole is a big number. Avogadro's number is really big. So it doesn't have to be like a full 1% difference. That's per 100 molecules or per 100 things, however we define that. And what we're talking about is moles could be, moles are in the 10 to the 23rds. So if we have a mole, just a smaller fraction of that, of a slight excess, could lead to deracemization. So that's that first step, is deracemization. In the second step, we're going to go from a slight excess to a huge excess. And that's the step called chiral amplification. So in chiral amplification, we amplify or exponentially increase the ratio to strongly favor one enantiomer. Okay, so if we were at 51-49, and again, that's called a scalemic mixture, a slight excess of one enantiomer over the other, not perfectly racemic. In chiral amplification, we go to something like 99.99 to 0.01 as a ratio of enantiomers, where now the 99.99%, maybe I should label these as percentages, now strongly favors one enantiomer. Okay, so we've achieved a slight excess, then we amplified that slight excess to a huge excess. This is almost a separate step, okay? And then with number 3, in step 3, we achieve chiral transmission. And this is what I focused a lot of the last lecture on. Chiral transmission is where we take homochiral molecules and we allow them to transmit their homochirality into the generation of other chiral molecules. So homochiral molecules transmit their homochirality / use their homochirality, maybe use is better, use their homochirality to generate single enantiomers / homochiral samples. Let's just say homochiral samples of other chiral molecules. Okay, so we want to generate homochiral samples of other chiral molecules. And so a big example of this is where we have chiral amino acids make chiral catalysts. And these are our enzymes. And the functional diversity of enzymes is used to produce other biomolecules. So it makes other biomolecules. And it's this process of using chiral amino acids that are now single enantiomers because we amplified the chirality, the nature that we're only going to see one enantiomer. We amplified that up so that it so much strongly favors one enantiomer. Then we built catalysts out of these. And remember, we have to start with something that's homochiral to get products that are homochiral. That something doesn't necessarily have to be the starting material that we do stoichiometry on very carefully, where we, for every mole of starting material we have, we can generate 1 mole of product. Because catalysts are regenerated after they're consumed, we can use small amounts of catalyst, small amounts of these things that harbor our homochirality, which we can then transmit on to the generation of new molecules now that are homochiral. So this is how we achieve homochirality in the universe. We do the Miller-Urey reaction to generate a racemic sample of many molecules that are useful in biology. And then something happens to deracemize the system, amplify the system, and then we start to build catalysts. It's the chiral transmission we see all the time right now. It's the amplification and the deracemization steps that we're not fully able to replicate in the laboratory to give rise to homochiral samples of molecules that life could use. So hopefully this was a nice wrap up to chirality. I think we're for real done, but I think I should also stop guaranteeing when we're done with the topic. So the videos are the videos. Anyway, okay, so we're going to move on to another topic called arrow pushing in the upcoming lectures.